Alright, so this is the last problem set on the lecture on hypothesis tests, and we have here a two-sample t-test assuming unequal variance. So we have again two groups, and they are the couch potatoes and the sports nuts. So let's call them couch and sports. And we have statistics for those two samples. First we have the N, and the average monthly expenditure on chips and soda for a random sample of 25 couch potatoes revealed a mean expenditure of $112 and a variance of $100. Okay, so the average monthly expenditures of a random sample of 36 sports nuts on chips and soda was only $100, and the variance was $432. So this is the data that we work with, and again it says we can assume an equal variance, so you don't have to conduct an F-test. But again, we can also conduct an F-test just from that variance. And I just want to show that to you quickly, which might be helpful later when we talk about ANOVA and to get a feeling for F distributions. But what we do is we typically calculate an F statistic, which consists of the larger variance, which is the 433. So the variance, which whatever is larger, that goes in the numerator. And we divide that over the variance of the smaller. So our F statistic that we test for in an F distribution, and an F distribution, you can think of it as also a right tail. And then we have a F test statistic. So what we do is we divide the greater variance by the lower one. And that is our test statistic that we test in a test. Okay, so it might be a little bit confusing that we also have a two-tailed test here. A F distribution often looks like this with a long right tail. Okay, so now what we test is we have a value here of 4.32. And I'm interested in this area to the right. And even though this seems to be a case where there is actually no symmetric right tail, symmetric left tail, we nevertheless multiply it by 2. And let's first do that. So the P value associated with our F stat is 4.32. So now we would say F, and then there is an Excel formula, F dot dist right tailed. So now we want that 4.32, and now we need to know the degrees of freedom in the numerator. So that is 35, because we have an N of 36. So in the numerator we have 35. So our sample of the sports nuts, we have 36 observation, and then the mean, so the degrees of freedom there is 35. And for the couch potatoes, it's 24. So the degrees of freedom are, degrees of freedom 1 is in the numerator, degrees of freedom is in the denominator. Okay, and I have to multiply that by 2. But let's first take a look at it, what we get. So it's a very small number. And even if you multiply times 2, there's such a small probability so that we can clearly assume that those variances are unequal. Again, in an F-test, the null hypothesis is that variance couch potato is the same as the variance of the sports nuts. And the alternative in a one-tail test is, in a two-tail test, is the variance of the couch potatoes is unequal to the variance of the sports nuts. So now you may be probably surprised that how can we do a two-tail test if things do not look like typically like this. Because the variance is always squared, we can never have any negative values. Well, the point is, the other tail would be that I don't do the larger variance divide by the lower variance, but I can think theoretically, nothing keeps me from doing an F-stat where I calculate the lower variance over the higher variance. So in this case, I would get an alternative where the value is something like this. So 0.23. So now let's say the 0.3 is here. Then what we will calculate is now this area, and this is the area that you can think of as the second tail. It's not exactly the same. Under certain circumstances, the area to the right would be the same as the area that you see to the left when you use the reciprocal value, but it's a good proxy and good enough. And if you don't want to do a two-tail test, we have already seen if we do a one-tail test, we will clearly reject equal variance. But anyhow, so much about the F-test, and again, we will talk more about that when we go into ANOVA. So not only can we assume now an equal variance, we also have seen it in an F-test. Okay, but now we want to see, is there a difference? Do the couch potatoes statistically significantly spend more? And actually, here this calls for a two-tail test. So is there a statistically significant difference? So, but let's first calculate this difference. So if I do a couch potatoes average minus the sports nuts, then the mean difference is 12. So that is the mean that we test for. So our sampling distribution, and we still need to calculate the standard error and the degrees of freedom. And for this we have to use this formula. But just the intuition of the test, we have a sampling distribution and we assume that our H0 is that couch minus sports is equal to 0. But then we got an average couch minus sports, which is equal to 12. The question is, how much does that translate into t-score? So a 12 is how many standard errors above a 0. Okay, so the first solution is obviously P or C, because we don't have any sigma, it's again a T. Okay, how many degrees of freedom do we have? So now we need to use this formula here, which is quite complicated. And so what I will do is I create again a degree of freedom calculation. And the first thing I do is I calculate for the couch potatoes and the sports nuts the ratio of the variance to the sample size, which is s squared divided by n. And then I make sure that it reads as squared, so I highlight the 2 and I go to 4 and I superscript it. Okay, so for the couch potatoes, again here couch, sports. So the variance is the 100 divided by the 25, so that's 4. And for the sports nuts, 432 divided by 36, so that's 12. And so now I just focus on so now I have always the s squared over n for the couch potatoes and the sports nuts. So now I just focus on the numerator, and the numerator is equal to, open parentheses, the s squared over n for the couch potatoes plus the s squared over n for the sports nuts, and then we raise that by 2 or square it. So now in the numerator we have a value of 256. Now I focus on the denominator. I mean, you can write it in 1, but then you're more likely to make a mistake. So for the denominator we have to first square again the s squared over n value, then divide that by the degrees of freedom, which is 24, 25 minus 1, and then plus the s squared over n squared again divided by the degrees of freedom of the sports nuts, which is 35. Oh wow, okay, so now in the numerator we have, so is this correct here? I think that ratio will be so huge. Okay, yeah, that's correct. Okay. So the degrees of freedom are 256 divided by the 4.7. Okay, so now we have to round up. So we have 54 degrees of freedom. So you always round up. So we have 54 degrees of freedom. So degrees of freedom, we have 54. So now I can look up the critical T for a two-tailed test. So I need to find the T where I have here 2.5% to the left, and here I have 2.5%. All right, so we call that critical T equals, we use T dot inverse because it's now alpha half, so 0.025. Degrees of freedom 54. So our critical T is essentially negative 2.005, negative 2.005. 5, and to the right it is positive 2.005. So our critical T is plus minus 2.005. Okay, so now what's the standard error? That's relatively easy. So the standard error actually is, I can put it here, SE equals, so that's the square root, open parentheses, of the 4 plus the 12. So that is 16 over 4, so we should get 4. So the standard error is 4. Oh, okay. So now we can see that the standard error of our sampling distribution is 4. And then the standard is 4. So our test statistic is our t test. Well, that's the 12 minus the 0. So how far is that away from 0? Well, 12 over our standard error of 4. So now we get a very nice test statistic of 3. And we can see that so we have a situation that this t corresponds to a test statistic of 3. So we clearly reject the null, and the conclusion is we reject the null. But we could have made a type 1 error. And again, the type 1 error in a two-tailed test now is that this is the probability that we can actually draw a sample of couch potatoes and sports nuts, even if there's no difference in the chips and soda consumption, that we find two samples, that we can draw two samples from those populations that actually suggest such a difference of 3. And then we must not forget to multiply that times 2, because in a two-tailed test we assume that also to the -3 we need to account for that probability as well. Okay, so what is the p-value? The probability that we made a type 1 error. The p-value is equal to, so now we use t.dist, degrees of freedom, x is -3, and degrees of freedom, we said 54, and I want it cumulatively, and that should be a very small number, and I have to multiply times 2. So that's 0.5% roughly. So the probability is 0.004, or 0.4% roughly. So it's a very small probability that we made a type 1 error, but it is a probability. Okay, so that concludes the problem sets and also the lecture on hypothesis test. And yeah, I just hope that you understand the concept and feel comfortable with Excel now. And yeah, so that's it, and I'll see you in the next topic.